In the last couple of videos about quantum physics, we have seen how light, which has traditionally been considered to be a wave, under certain circumstances behave like a particle. So, for example, in an experimental setup uh, to study photoelectric effect, we find that light actually behaves like particles known as photons. And then we also saw that in Compton scattering, when you have X-ray photons uh, collide with electrons, then the resulting final energies and momenta of electrons and photons again point to the particle nature of these photons of light or electromagnetic radiation. Now, if electromagnetic radiation, which is traditionally thought of as wave, can under specific circumstances exhibit particle-like behavior, then if you assume a symmetry in nature, then one would wonder, well, if what is thought of as wave can behave like a particle, can you have the reverse of that, meaning objects, things that are considered to be particles, can they behave like waves? And the answer is yes. De Broglie, a French physicist, was the first one to think about this, and he basically used the equation that we had. The equation was P equals H over lambda, which showed the particle-like behavior of waves. So if you have a wave of wavelength lambda, it behaves as if it has a momentum equal to Planck's constant divided by that wavelength. So that's the equation we saw, P equals H over lambda. So what de Broglie did was basically just solve that equation for lambda, and then you get lambda equals H over P. So essentially what we're saying is, if you have a particle of momentum P, then it can behave as if it's a wave of wavelength lambda given by H over P. So this equation works for both matter as well as photons. It works for waves as well as particles. In order to see wave-like behavior, that is interference, which we talked about briefly in the previous video. Things have to interact in order to see this interference-like behavior. Things have to interact with matter of the size comparable to their wavelength. Just to remind you of what this interference was, let me pull up this diagram. So if you combine two different waves, this is wave one at the top and wave two at the bottom. When you combine them, if their peaks occur at the same time and their valleys occur at the same time, then the combination, the resultant of these two, is a much bigger wave. So they reinforce each other. And this is called constructive interference. On the other hand, when you combine them, then and the peak of one coincides with the value of the other and vice versa, then when you combine them, you basically get no wave. They cancel each other out. So the resultant is nothing. If these were light waves, then you would say that in constructive interference, you see a bright spot where the two waves reinforce each other, and you see a dark spot where the two waves cancel each other out. So this is the basics of interference. And in a double slit experiment used to study interference, you basically have light from two different sources. Well, there are two different slits. There's a common source which hits the two slits, and then there's a wave front coming from slit one and a wave front coming from slit two. And then if you look at them on a screen of how these lights propagate, how these waves propagate to the screen, then depending on how much path they have traveled, they may either be in phase, peaks and valleys coinciding, then you will see a maximum, meaning a bright spot. However, if they're out of phase, meaning peak of one coincides with the trough of the other, then they will cancel out and you'll see a minimum. So in interference pattern, you basically see alternating dark and bright spots, something like this. Now, in order to see a good interference pattern, the wavelength of light and the width of the slit have to be comparable to each other. So in order to see wave-like behavior, in order to see interference, things have to interact with matter of the size comparable to their wavelength. So if you're talking about light going through slits of width, which are about the same or in that ballpark to their wavelength, then you will see an interference pattern. For larger objects, if the slits were much bigger, waves would just travel in straight line like it does in geometric optics. When we draw ray diagrams with a lens or a mirror, we just draw light as traveling in straight lines. So in this case, for example, if the width of this slit and this slit was much bigger than the wavelength of light, then when light hits from the left, that light would simply just travel along a straight path. And you won't see any bright and dark spots. All you will see is one bright spot here and one bright spot here. Now, if you talk about the wave-like behavior of macroscopic objects, does a 3-kilogram bowling ball, can it behave like a wave? Well, the answer is yes, but let's think in terms of the practicality of observing that wave-like behavior of a bowling ball. So if it has a mass of 3 kilograms and if it's moving at 10 meters per second, then we know its momentum is 3 times 10. So the wavelength of this bowling ball would be Planck's constant divided by the momentum, and it comes to 2 times 10 to the negative 35 meters. And what that means is, in order to see the wave-like behavior of a bowling ball, you would have to be able to squeeze this bowling ball through slits, which are this wide, 2 times 10 to the negative 35 meters. And obviously, that's not possible. So that's one reason why you don't see wave-like behavior of macroscopic objects in day-to-day lives. That, again, it goes back to the size of the Planck's constant being so small. So we don't see quantum effects in our day-to-day macroscopic world. Two physicists by the name of Davison and Germer, they did an experiment where electrons were scattered. You send a beam of electrons to hit crystals, and then these electrons are scattered, and the molecules in the crystal behave like, or the pattern in a crystal behaves like a slit. So the electrons can either go through the crystal or collide against the molecule. So essentially, it behaves like a slit. A slit with multiple openings is called a diffraction grating, and the interference pattern that you form with a diffraction grating is called a diffraction pattern. So they scattered electrons from a crystal and they found a diffraction pattern, and they did measurements on the spacing of the bright and dark spots, and it all was consistent with this equation, lambda equals h over p, basically meaning that these electrons scattered from crystals behave exactly as if their wavelength was Planck's constant divided by their momentum. So that was a confirmation of wave-like behavior of electrons. Electrons that we traditionally consider to be particles can, under certain circumstances, under the right kind of experimental setup, can behave like waves. Okay, let's consider problem number 54. So problem 54, experiments are performed with ultra-cold neutrons. Ultra-cold neutron basically means neutrons moving at small speeds. So experiments are performed with ultra-cold neutrons having velocities as small as 1 meter per second. And we have to figure out the wavelength of such a neutron and its kinetic energy in electron volts. For the wavelength, we can just use de Broglie's equation, de Broglie wavelength. It's moving at obviously a non-relativistic speed, 1 meters per second, so we can use the classical equation for momentum. Mass of a neutron, we can look it up, is 1.675 times 10 to the negative 27 multiplied by the velocity 1, and then you divide Planck's constant by that. And this comes out to 3.96 times 10 to the negative 7 meters, or 396 nanometers. So it seems like a wavelength around ultraviolet part of the electromagnetic spectrum. Okay, and then for the kinetic energy, again, we can use the classical equation. Kinetic energy is 1/2 mv square. So you get that. And this is going to give you kinetic energy in joules. And then we can convert it to electron volts by dividing by the charge of the electron. So this is the energy, kinetic energy of this neutron in electron volts. An interesting application of this wave-like behavior of particles, specifically electrons, is in the construction of a microscope. Now, traditionally, images are formed. Basically, these are light images. So light travels through lenses and it's magnified and so forth. The objects are magnified and so forth, and that gives you large images. In electron microscopes, instead of using light, we actually use beams of electrons to magnify the image of an object. The resolution of images, meaning like how small of an object can you see, are of the order of the wavelength of the signal being used. So with just a potential difference of 50 volts. So basically the experimental setup of electron microscope is as follows. You have a source of electron and you eject a beam of electron from there. And then you have all kinds of mechanisms to have a focused beam. On the other side, on a plate, you have the specimen that you're trying to magnify, that you're trying to look at through a magnified image. And then these are connected to some electronic circuitry, and you can see the image on a screen. So with just a potential difference of 50 volts, you're able to produce electrons of wavelength which are less than a nanometer, less than a nanometer, which is, which is obviously quite small. And as we saw in that picture, the focusing of electron beams is done with magnetic fields. And with just this potential difference of 50 volts, you can produce electron beams which are able to magnify images by a factor of 100 million. So you can, with very little effort, you can create highly magnified images. And what you see here, this is the image of the tooth of a dinosaur seen under an electron microscope. Okay, so we know that particles, you can associate a specific location with a particle, that this is where it exists. Whereas waves, by their nature, travel and they spread. So waves have spatial spread. And if matter is wave, then where is it located? So if you can associate a wave with an electron, then where exactly is the electron located in that wave associated with it? Experiments show that electron is indeed at a specific location, but repeated measurements will find the electron in different locations. So the electron does exist at a specific location, but what that location is will vary depending on the observations and the experimental setup. So a statistical distribution of locations is seen with wave-like appearance. Let's look at figure 2925. So what you see here is the result of a double slit experiment. So instead of light hitting the two slits, or a diffraction grating, which is multiple slits, instead of light hitting the slits, you have a beam of electron which hits the slits. And again, what you would expect is, if you have a beam of electron going to the right here, then you would expect, some of the electrons will go through this slit and they will accumulate, or they'll be found here. And then rest of the electrons will go through this slit, and then you'll see a whole bunch of electrons there. And that's all. However, if electrons can behave like waves, then you should be able to see electrons over the entire screen. You will have constructive interference, you will have destructive interference. So in some places, you'll see a whole bunch of electrons. In other places, you won't see any electrons at all. And that's exactly what's observed. So what you're seeing here is that pattern, that interference pattern. So if you have a beam of 40 electrons, this is what is observed. You see a bunch of electrons here, a bunch of electrons here, nothing in between. And then as you increase the number of electrons, this maxima and minima, so to speak, bright and dark spots become more and more prominent. And whether you do this experiment with protons or electrons, you see similar kind of interference pattern. So this, proves again the wave nature of particles, the wave nature of electrons, and the wave nature of protons. And if you measure the spacing between the bright and the dark spots, and you do the calculations, you find that those spacings between maxima and minima, or bright and dark spots, is consistent with de Broglie wavelength. So these electrons and protons are indeed behaving as waves of wavelength given by lambda equals h over p. Now, these are statistical patterns, meaning like if you have 2,000 electrons, you notice that they tend to bunch into these points of uh, brightness and darkness, so to speak, but you cannot figure out the exact path that an individual particle has taken. You cannot predict that. You can only predict that you will have bright and dark spots or a bunching of particles in these regions, but you cannot say exactly how a specific particle is going to travel. And the pattern is observed even if the intensity of the beam is so low that a single electron passes through. And that's something quite remarkable. So instead of 40 electrons or 200 or 2000, even if you have a single electron hitting a double slit setup, if you have a single electron moving to the right, you still see the pattern. So it's as if a single electron is interfering with itself, or a wave associated with a single electron is interfering with itself, causing bright and dark spots. And that's something, you would obviously never expect in classical physics. So that's another of a very unique feature of quantum physics. Now, let's say you try to be clever and try to figure out the exact path that that single electron has taken. So again, you're shooting a single electron to the right, and you place detectors here, and you're able to see a pattern here. Now, if you take those detectors and say, okay, I'm going to put a detector in this slit and this slit, and try to see which of the two slits did the electron go through. As soon as you install the detectors or the slits, the interference pattern disappears altogether. So it's as if nature is saying, I'm not going to manifest myself if you're trying to cheat me. So if detectors are used to determine which slit did the electron go through, the double slit pattern turns into a single slit pattern. So all you see is a bright spot. All the electron is focused in just one point. So this wave-like behavior of particles points us towards an inherent uncertainty in nature. And that is captured by what's called Heisenberg uncertainty. Heisenberg was a German physicist who did research in this area. The underlying principle of Heisenberg's uncertainty principle is that the idea that if you make a measurement, then you're liable to affect what you're trying to observe. Now, in order to observe anything, in day-to-day lives, we shine light on it and the light bounces back and we see the reflected light and we are able to see the object in question. So imagine now shining a beam of light to observe an electron. Now, when the photons of this light interact with the electron, they're going to scatter the electron. They're going to disturb the electron. So thereby, it's going to introduce an uncertainty in the position of that electron when you're trying to observe it. So measurement affects the system that you're trying to observe. And an extension of that is it's impossible to measure certain pairs of quantities simultaneously to exact precision. So for example, to measure the position of a moving electron, if you try to measure the position of a moving electron, you can scatter light off of it, but that's going to change the electron's momentum. When the photons hit the electron, they're going to change the momentum of the electron. So to make the precision of position measurement greater, the wavelength of scattered light needs to be smaller. You have to have a smaller wavelength in order to say more precisely where the electron is located. But then when you do that, you're increasing the momentum of the photon and thereby increasing the uncertainty of momentum. So essentially, position and momentum are a pair of quantities. If you try to increase the precision in position measurement, you lose precision in momentum measurement. And if you try to increase the precision in momentum measurement, you lose precision in position measurement. Now, this may seem like it's something that could perhaps be overcome by better technology. If you have better technology, maybe you can measure both of those quantities precisely at the same time. But it turns out this uncertainty is inherent in nature. That's the nature of reality, and you cannot overcome that handicap simply by using better tools. So even in principle, there's a limit to how much you can learn about nature. There's a limit to absolute knowledge. So Werner Heisenberg was the first to recognize and quantify these uncertainties. Uncertainty in position is of the order of the wavelength, and to detect the position of a particle, it needs to interact with a measuring device. In this interaction, however, it loses some or all of its momentum. So it's, again, the idea of photon and electron interacting with each other and changing each other. So uncertainty in momentum may be as large as momentum itself. So delta P is the uncertainty is equal to h over lambda. And then if you delta x times delta P from here, you can show that is equal to the Planck's constant, meaning the product of the uncertainty in position and uncertainty in momentum is at least equal to h over 4 pi. It could be greater than that, but at least equal to that. So that's one formulation of Heisenberg's uncertainty principle. Delta x delta p is greater than or equal to h over 4 pi. Again, delta x here is the uncertainty in position measurement, and delta p is the uncertainty in momentum measurement. If you increase one, the other one decreases, and vice versa. Again, this is not noticeable in everyday life since h is so small. This is so small. So the uncertainty in the macroscopic world is very, very tiny. We don't even observe it. There is another pair of quantities which obeys Heisenberg's uncertainty principle, and that's energy and time. So if you're trying to measure energy and time at the same time, then the uncertainty in the energy measurement and uncertainty in time measurement, delta E and delta T, will also be bound by this inequality. Delta T is the time needed to make a measurement, or the amount of time an unstable particle exists. So there you can look at it in different ways. What is delta T? Delta T is the time you need to make a measurement, or the amount of time that an unstable particle exists, after which it dies or decays. So if you consider particles that have a lifetime of, say, 10 to the negative 25 seconds, very short-lived, then according to uncertainty principle, this inequality, delta E would be of the order of 10 raised to 9 electron volts. So that's a large amount of uncertainty in the rest mass of this particle. Another consequence of this inequality is that now we know that conservation of energy is a bedrock principle of physics, and it's always supposed to be valid. However, if this inequality is true, if delta E delta T can be greater than or equal to h over 4 pi, what that means is energy conservation may be violated by an amount delta T for a period of time by an amount delta E for a period of time delta T given by this inequality. So in other words, you can violate principle of conservation of energy for a very short period of time. And one consequence of conservation of energy is that you cannot create energy out of nowhere. However, if you can violate conservation of energy for a short period of time, that would suggest that you can create short-lived particles out of nothing without providing any energy. You can create these particles. They will live for a very short period of time, but they can exist. You can create them. Okay, let's look at problem number 64. Problem 64. Suppose the velocity of an electron in an atom is known to an accuracy of 2 times 10 raised to 3 meters per second. What is the electron's minimum uncertainty in position? And how does this compare with the approximate 0.1 nanometer size of the atom? So we collect all the information. Delta V, uncertainty in velocity, is 2 times 10 raised to 3, and we're looking for delta X. So using the limit, the lower limit on delta X equals h over 4 pi times delta P. And then using momentum as mass times velocity. So delta P is m times delta V. And then you plug in the values. Here is the mass of the electron, 9.11 times 10 to the negative 31. That's the uncertainty in velocity, that's the Planck's constant. And we come up with a value of 29 nanometers. So if an electron is, if you can know the velocity of an electron accurate to 2 times 10 to the 3 meters, then the position of the electron cannot be known better than 29 nanometer. And then how does this compare? How does this compare with the approximate 0.1 nanometer size of the atom? So you just find the ratio of the two. 29 nanometer divided by 0.1 nanometer comes to 290. So 290 times the size of an atom. So this uncertainty in the position of this electron is so huge. It's 290 times the size of the atom itself. And remember, this electron is inside the atom. So if the atom is over here, the electron can be anywhere over a space of 290 times the size of this atom. So it's pretty remarkable. All right, let's look at problem 69. The decay energy of a short-lived nuclear excited state has an uncertainty of 2 electron volts due to its short lifetime. What is the smallest lifetime it can have? So delta E here is 2 electron volts, and we have to find what delta T is. Again, we use the uncertainty equation, the lower limit on delta T, plug in the values. Now, you can approach this a couple of ways. You can either use the value of Planck's constant, which involves electron volts, or you can use the one with joules, but then you'll have to convert the energy into joules. And the conversion factor is the charge of the electron. So 2 electron volts is 2 times 1.6 times 10 to the negative 19 joules. The time, the uncertainty in time comes out to 1.6 times 10 to the negative 16 seconds. So that's the smallest lifetime this excited state can have. That completes our discussion of quantum physics. And we'll move on to the next chapter in the next video.